Welcome to Hartman Math. Today we're going to take a look at complex numbers, which brings in imaginary numbers, starting by looking at the imaginary unit I. If we were to look at the equation x squared plus 1 equals 0, and we subtracted 1 on both sides, so x squared equals negative 1. Well, the problem is there are no real numbers that we can square and get negative 1 or any real number. So we have to go outside of the real number system and bring in imaginary and complex numbers. So we just define the number I to be the square root of negative 1. So that's a definition. In person, we like to give quizzes where we say, what is the square root of negative 1? And I is the only acceptable answer. Always has to be fully simplified. Some people will write 1i. Some people will write I square root 1. Wrong, wrong. You need to be fully simplified. Just by the definition, the square root of negative 1 is I. That is the imaginary unit. And then if we start looking at I to integer powers, and we're going to focus on whole numbers here. Well, I squared, if we square both sides of this, square the left, square the right, squaring a square root just undoes that, we would get negative 1. And of course, I to the first power, anything to the first power is itself, so I to the first power is just I. And then I to the third power, we can use what we know about exponent properties and say, well, that would have to be I to the first times I to the second, which means it's I times negative 1, and that would be negative I. You do something similar for I to the fourth and say that's I squared times I squared, and therefore negative 1 times negative 1 would be positive 1. And if we did I to the fifth, there's different combinations we could use, but probably the easiest might be I to the fourth times I to the first. 1 times I is I. So we start to see, hey, it's going to repeat. In fact, if we did I to the sixth, you'd see it's the same thing as I to the second. I to the seventh is the same thing as I to the third. So there's really only 4 possible values you can get by raising I to an integer power. We're either going to get I, negative 1, negative I, or 1. So how might we go about figuring out which of these things I to the 555th power would be? Well, since there's a group of 4, it's a cycle of 4, and it is repetitive in a group of 4, I think what we should do is take the 555, we should divide by 4. Not on a calculator, not getting a decimal, but actually like regular long division. So what is 4 dividing into 555 long division style? Well, what you would get is 138 remainder 3. Remember when you first learned long division, you might have seen the remainder part. And that's actually what we're looking for here, because the remainder holds the key to the problem. Since the remainder is 3, I to the 555th power is going to be the same thing as I to the third power based off of the remainder. And I to the third power is negative I. So you're going to see why in a second that works. One other thing, you could get a remainder of 0. So if we work this backwards, I to the 0 power, well, remember, anything to the 0 power is always 1. That's the 0 exponent property. So that takes us back to the same thing as I to the 4th power. So really, your remainders could be 0, 1, 2, or 3. Now, why is that the case? What does all of this have to do with this problem? Well, it's grouping with this I to the 4th power. So what we're basically saying is I to the 555th is just I to the 4th raised to the 138, because if you were raising a power to a power, we would multiply the exponents. If I multiply this by 4, I get 552. with I to the third left over. So I to the fourth is just 1, so this is 1 to the 138th. And 1 to any power is 1. So 1 times I to the third, we get I to the third, which we know is that. Definition of a complex number. A complex number is possibly made up of a real part and an imaginary part. This is known as standard form a plus bi. I comes last. So if you're writing a complex number, just make sure you write the I last. Then it's probably in standard form. If you were to write something like 3 plus 2i over 5, that is not standard form, because I did not write the I last. I should have written 3/5 plus 2/5 times I. That would be standard form for that. So if b is 0, 0 times anything is 0, that washes away. We would get just a real number. When b does not equal 0, we get an imaginary number. And if it doesn't have a real part, so a is 0, then it's purely imaginary. So like 5i is purely imaginary, whereas 2 minus 7i would just be imaginary. So in terms of the complex numbers, they are made up of real numbers and imaginary numbers. All put together, we get the overall encompassing set of complex numbers. All right, so we're going to need to be able to perform some operations on complex numbers, adding and subtracting. Super easy. Notice it's an a plus bi form, a plus bi form. Could have given this problem in Math 1. You should be able to do it because it's really just combining like terms. We have 9 minus 6 for the real part, so 3, and then 2i minus 7i. Or we just distribute the minus, combine like terms, and we get our final answer of 3 minus 5i. That is standard form. Checkpoint, go ahead and pause the video here. This complex, this imaginary number plus this one minus this one. Make sure it's in standard form. Go. You should have gotten, if we roll out, everything kind of cancels out. We get 0. Is that a complex number? Yes, because all numbers are. Is it a real number? Yes, it's a real number. So that tells you when you add up or subtract complex numbers or imaginary numbers, you don't always get an imaginary number. This time we got a real number. All right, example 2, a little bit more fun, multiplying complex numbers. We have a purely imaginary number multiplied by an imaginary number. So we'll just go ahead and distribute. Okay, so multiply, multiply. That's not standard form. We're not allowed to have I squared, so go back to what we know about I squared and replace it. I squared is negative 1. So we're going to replace the I squared with negative 1. So this becomes 6i minus 14 times negative 1. So this is positive 14. And I do need the real part, which is the a part, in front. So that's got to go in front. Our answer, 14 plus 6i. Reminder that I needs to come last to be standard form. More multiplying. Part B. Now we're multiplying a imaginary by an imaginary. We're both binomials. So we're going to use our binomial multiplication strategy. Distribute the 6 to both. Distribute the positive 5i to both. So 36 minus 30i plus 30i minus 25i squared. These are like terms, and they can cancel out. I squared is -1. Negative 25 times -1 is positive 25 added to 36, and we get 61. That was kind of an important result here, where we got a real number by multiplying, and the only reason that happened is that these are conjugates, and particularly complex conjugates. The A's are the same, and the B's are the same except for their sign. Complex conjugates. All right, checkpoint, go ahead and pause the video here and do that problem. All right, you should have remember that squaring means to multiply by itself. 5 minus 2i times 5 minus 2i worked all out. I squared becomes -1. Those do combine to be -20i. That's a -4, which gets combined with the 25. There is our final answer. And our last operation with complex numbers is going to be quotient or division. And the result that we got back here is going to be the key to this, because we don't want our denominator to be imaginary. We need it to be a real number. So to make that happen, we use the idea of complex conjugates. So to fix the denominator and make sure that it's a real number, I need to multiply top and bottom, to be fair, by the complex conjugate of the denominator. Since the denominator is 4 minus 3i, we're going to need to multiply top and bottom by 4 plus 3i. Probably take some time to work through that, especially if this was a binomial on top, which it could be, just like kind of working through with example number 3. But here we would multiply on top and say 12 plus 9i over, and we know that since these are going to be conjugates, the I parts are going to cancel out, because we would get positive 12i minus 12i. So we're really just going to get 16 minus 9i squared. And since I squared is -1, -9 times -1 is positive 9. Combine that with the 16, we're going to get 25 as the denominator. So no i's left in the denominator. Now that's not standard form, because if we wrote this 12 plus 9i over 25, 5 would have been the last thing that I wrote. So I need to break this up and distribute the division. Divide both of these terms by the 25. So that's our standard form answer, 12 over 25 plus 9 over 25. And notice that the I is going to trail this B part, B times the I. Checkpoint, go ahead and do the division. Pause the video here until you're finished. Our complex conjugate for the denominator is 7 plus 2i, top and bottom. You're going to want to assume that this is in parentheses, so we do the binomial multiplication and simplify both. So our final answer, negative 5 over 53 plus 44 over 53i. All right, last thing we're going to take a look at is essentially solving some quadratic equations that don't have real solutions. So just a little bit of work. Something like if we were going to simplify the square root of -3, we could look at it this way, as the product of inside the radical, 3 times -1. So breaking that up according to our rules for radicals, that would be the square root of 3 times the square root of -1, which would be the square root of 3i. Now if you do write it like this, and that is standard form, make sure it's very clear that the I is not under the root. So maybe just push it out a little bit further to the right so that's very clear. Okay? And that's kind of demonstrating this. If we were doing the square root of negative 10, it's the square root of 10 times I. All right, so write the complex number in standard form. In example 5, one thought might have been, because there is a rule for radicals, square root of a times square root of b is you can just make it one square root and multiply them together. The problem with that, it was only true as long as both terms are not negative. But here both terms are negative. So we need to simplify, and then we will do the multiplication. So according to this, this is going to be the square root of 15 times I times the square root of 3 times I. And now we'll do square root of 15 times the square root of 3, and we'll do I times I. And the square root of 45 is 3 root 5, and this is negative 1, so 3 times root 5 times negative 1 is negative 3 root 5. So that idea we can use when we're solving quadratic equations, such as example number 6. Our first thought in example number 6 might be to try to factor. So we can come up with like 7x, 1x, and try to figure out where the 1 and the 2 go to multiply and give us the positive 2. But we're never going to be able to get the 5x there. So maybe we default to, well, let's just use the quadratic formula. So x equals the opposite of b, plus or minus the square root, b squared minus 4 times a times c, all divided by 2 times a. So we would evaluate here and say that's 25 minus 56. That's going to be negative 31. So previously we say, hey, that has no real solutions, and that's true. This is going to tell us it's going to have some imaginary solutions. So this just becomes square root 31 times I. And if we then distribute the division, negative 5 over 14, plus or minus, that's going to create two solutions, square root of 31 over 14 times I, because the I came out. All right, checkpoint, go ahead and solve this one. Pause the video here until you're done. All right, this one can also be done by the quadratic formula, but it's probably not the most efficient method. I would probably use completing the square. So if we did completing the square, we'd move over the constant. We figure out what number completes the square by taking half of negative 2 and then squaring it. We get 1, so we're going to add 1 to both sides. It then becomes a square root method problem. As we write this as a square, we did square the negative 1. That's why that goes next to the x. Square root both sides. Do not forget your plus or minus. The square root of negative 4 is the square root of 4 times I. And square root of 4 is 2. So 2 times I. So as we add 1, and I usually will do that in front of the plus minus, and that puts it into a plus bi form. There we go. That's it for today. I'll see you next time.